Hi, welcome back to My Smart Learning. It's been a while. This is a lesson for year 9s, but also relevant for year 10s and year 11s for your GCSE Physics as well as the Trilogy Science. So it's for all three sciences, but it's the physics element. We're looking at chapter 6 in your computer textbook, looking at particles. So it's the beginning of a new chapter, chapter 6 in the physics textbook on particles. So, what we're focusing on today is density. Decides to work. And our learning objective is how do we measure the density of solids and liquids. Recall quiz, obviously, you want to get your virtual high five. So number 1, what is the unit for mass? Number 2, what is the unit for volume? Number 3, how many grams do you get in a kilogram? Number 4, how many milliliters are in a litre? And number 5, which is more dense, a golf ball or a table tennis ball, a ping pong ball, or sometimes people call it whiff waff, a golf ball or a table tennis ball, and why? If you press pause on the video, have a go at answering those questions. And when you've unpaused it, we'll go through the answers now. Right, so the unit of mass is grams or kilograms. The unit for volume is actually centimeters cubed or meters cubed. I know people use milliliters because 1 centimeter cubed is 1 milliliter, but the correct unit for volume is centimeters cubed and or meters cubed. How many grams in a kilogram? That should be easy because you should do that in primary school. That's 1,000 grams per kilogram. How many milliliters are in a litre? Again, that should be straightforward. It should be 1,000 milliliters in 1 litre, which is the same as in 1 litre is 1,000 centimeters cubed in 1 litre as well. Okay, another unit for a litre, another way of saying a litre is a decimeters cubed, dm cubed. And the last one, which is more dense, a golf ball or a table tennis ball? Well, it's the golf ball, obviously. Why? Because you probably just say it's heavier, and that's true. A golf ball is heavier than a tennis ball. A table tennis ball, a ping pong ball. They're the same size, but the golf ball is heavier and therefore it's more dense. So it's to do with how packed the particles are, but we'll come back to that because I've got to put a little starter question for you. And that starter question is this: which is heavier? Is it a ton of feathers or is it a ton of bricks? So have a think about that. Which is heavier, a ton of feathers or a ton of bricks? Now I hazard a guess that most of you that have answered that question would have gone for the obvious, common sense, ton of bricks. A ton of bricks must be heavier than a ton of feathers because it's bricks and bricks are heavier than feathers. That's obvious. Everybody knows that. Even a little baby would know that. However, it's a trick question. If some of you have thought about this, it's a trick question. Neither is heavier. Wow, shock horror. What do you mean neither is heavier? Neither is heavier because they both weigh a ton. Now, how much is a ton? A ton is another unit. It's 1,000 kilograms. So if I've got a ton of feathers, that's 1,000 kilograms of feathers. And I've got a ton of bricks, that's also 1,000 kilograms of bricks. So they're both exactly the same weight. They've got the same mass because they've both got 1,000 kilograms of stuff. And this is a bit of a misconception, a little trick question. Why? Because bricks are obviously more dense than feathers because bricks weigh more. So what is density? Density is about how packed or how condensed those particles are and how much individually those particles weigh, how closely they're packed together. The more closely you packed these particles together, the more dense it will be. So for instance, gases have a lower density than compared to a liquid, than compared to a solid, because solids usually are the most compacted, therefore the heaviest, and therefore have a higher density. Feathers, for instance, they are solids, but there's lots of air spaces between them, so therefore that mass is spread over a given greater volume, greater space, and therefore it's got lower density. So density is not just about how heavy something is, it's basically how packed those particles are together. The more packed they are close together, and if individually those particles weigh more, therefore there'll be a greater density. Ping pong ball, same size as a golf ball, but the ping pong ball is hollow. It's got there's air in there, so the air's got low density compared to and the plastic's just on the outside case. Whereas a golf ball is packed full of whatever's inside a golf ball. I've never cut one open, but it's more dense. So here again, the feathers have a lower density than bricks, but if you've got the same amount of mass of stuff, 1 ton, they both have the same. But a ton of bricks may only be, you know, so many bricks, you know, square meters wide. All right, it might fill up, a ton of bricks might be just literally maybe the size of this TV in a big cuboid. That might be a ton of bricks. But a ton of feathers might fill up my entire living room space. Okay, the entire room might be full because to make the same amount of mass. So, how do I calculate density? Well, density is measured in centimeters cubed or kilograms per meters cubed. That's the units of density. So it's the unit of mass divided by volume. So it's the mass per given volume. That's the definition of density. Density is the mass per given volume. So the given volume, if I do it per meters cubed or centimeters cubed, it will either be grams per centimeters cubed or it will be kilograms per meters cubed. So it's the mass divided by the volume. So that's what density is. But the symbol we use for density is this funny little P shape. It looks like a little P, slanted P. It's actually a Greek letter. It's a lowercase for rho. Now, what do I mean by rho? It's just a Greek letter like alpha, beta, gamma, omega, pi, psi. These are letters of the Greek alphabet, and we use them in mathematics and we use them in physics for symbols for equations and formulae. So, for instance, this looks like a P. It's just slightly off-centered. It's kind of slightly across a bit, but it represents density. So density is the M divided by V, the mass divided by the volume. And you must learn that formula and memorize that formula, not just for your GCSE Physics and Science, but also for GCSE Maths, because they do ask you questions about calculating density. So this is cross-curricular. It comes up in your GCSE Maths paper. It's also in your Physics GCSE paper too. So to work out the density is the mass in kilograms divided by the volume in meters cubed, or it could be the grams per centimeters cubed. And the density is just the mass divided by the volume. And it's in a little formula triangle. So density is mass over volume. Therefore, if it's mass over the volume, if you imagine if I got this in a triangle, the mass goes at the top, the density is down there. So to work out the mass, it'll be density times the volume. So if I shift this up, density times the volume will give me the mass. And if I wanted the volume, it'd be the mass divided by the density. Okay, so how do I work out the density then? Well, for an object, if I want to work out the density, first of all, I need to find out its mass. Now, how do I find out the mass of a regular solid object, like, let's say, a cuboid? So just a block of wood or a brick, let's just use the example of a brick, a solid brick that's completely flat all the way around. How do I work out the mass of it? Well, I can just put it on some scales. A top-pan balance is the correct term for it. A balance or a top-pan balance. If you weigh it, it'll give you the mass in grams, or if you set it in kilograms, it'll give you it in kilograms. So you'll get the mass in grams. So to weigh, so that's our answer, how we get the mass. How do I get the volume then? Well, for any regular shape, you need to know your formulae. So your formulae for regular objects, how do you work out the volume? So if it's a cuboid, it's length times width times height of that cuboid. If it's any type of cylinder, you need to work out the surface area of the circle, then you multiply it by how long that circle is. So that's your cylinder. So pi r squared gives you the area of a circle. You times it by the length of it or the height of it, however long it is, and that'll give you the volume of a cylinder. If it's any type of prism, these are both particular types of prism, any type of prism, all you have to do is work out the surface area of the face and multiply by how long that face is, and that'll give you the volume of a given prism. Now, here's a couple of examples. What are the volumes of these cuboids? Well, here's a cuboid. How do I work out the volume? So it's length times width times height. So all I do is I do 6 times 3 times 2. Okay, so 6 times 3 is 18. 18 times 2 will give me 36. What about this one? Can you work this one out? The volume of this cuboid, again, length times width times height. So again, 10 times 4, which is 40, times 2, which equals 80. 80 what? Well, both of them are in centimetres, so the volume will be in centimetres cubed. So there we go, we've got 36 and we've got 80 centimetres cubed. What about if you got funny ones like this? Well, if you've got a missing length, the volume is this times this times this, so there's a missing number. So to work the missing number out, what you'd have to do is you'd have to multiply those two together and then divide the volume by that to get the missing number. You do what we call the inverse. So you'd have to multiply your two numbers, leave the missing one out for a second, and you divide it by your volume, because your volume is the length times width times height, and that'll give you your answer. So what would the answer to this one? Well, you've got 36 divided by 2 times 2, which is 4, so 36 divided by 4, so that answer must be 9. And this one, I've got 70, but there's a missing number there, so 5 times 2 is 10, 70 divided by 10, that one must be 7. But 7 what? So remember, so we said that was 9, 9 what? It's 9 centimetres, because the lengths are in centimetres, the volume is in centimetres cubed, and that one must be 7. Now, then you can do the practical. Now, this is a required practical for your GCSE Physics and your Trilogy Science, so you have to do this practical. You'd get a top pound balance of scales, which you'll see in a second, and you weigh your block. You measure the mass of the block, so you write down what the material is. It could be a piece of wood, it could be a piece of granite, or marble, or block of steel, or copper. What's the material? What's the mass? You can measure the length times the width times the height. Multiply those three together will give you the volume. Then you do your mass divided by your volume, and that will give you your density. And here's some results that we got from class when we were back at school. So for class 9U that I taught before the lockdown, we actually did this practical and some results that we got from the practical. Some of the other classes like 9Q, I don't think you got to chapter 6 yet on particles, so you'll have to do this again at some point and make sure you've done the required practical. So it's the mass divided by the volume gives you your density. So these were little cubes. You can tell they're cubes. Why? Because the length times the width times the height are exactly the same. So it's a cuboid. It's not cuboid, sorry, it's an actual cube, because it's length times width times height. They're all the three same numbers. So the volume was 8 centimeters cubed. Now if you notice, all of these numbers, or most of them, are above 1. If any of the numbers are above 1, that means they have a greater density than water, because water's density is 1 gram per centimeter cubed, or 1 kilogram per litre per decimeter cubed. So water's mass is 1. Anything that weighs more than 1 will sink. So a block of steel, or a block of aluminium and copper, they will sink. All those metal blocks will sink. Whereas the non-metals, they're like polythene and wood, they're less than 1, they will float. So if it's greater than the density of water, they will sink. If it's lower density, it will float. So that's the first practical. The next practical, so that's the first required practical. The next practical is you need to know the density of irregular objects. So we just talked about regular objects where you've got a ruler and you can just use the ruler to measure the length times the width times the height to measure the volume. You measure the mass, weighing on a top pound balance. You divide the two numbers, it gives you a density of your regular objects. But how about if the object is irregular, like a liquid, or an object that's like a rock that doesn't have a regular shape where you can get a ruler and measure it equally all the way around? Well then, the two other parts to this investigation is the measuring the density of liquids and irregular objects. Story time. Have you heard of the story about the king and Archimedes? Okay, Jackanory story time. So, legend has it, you probably know this, you may have heard the story before, probably in horrible histories or something. There was, a long time ago, there was a king in a far, far, far away land. And this king had a problem. His problem was this, that he wanted a crown made from his best piece of gold, which he needed to melt it down and make it into, you know, a crown. Now he didn't want to give his gold to his any old jeweler in the town, because he didn't want to get ripped off, because there are other metals that look like gold but are not gold, because gold is a very precious metal because it doesn't rust. Whereas there are other things called like fool's gold, also known as pyrite, which is an alloy of iron. It's actually got iron in there, but it looks shiny and gold when you've got it fresh. And over time, it will start to rust and look more like iron. Now, the king didn't want to get fooled with fool's gold, it's called. So he wanted to make sure that the gold he'd given to the jeweler to make his crown would be the gold that he gave, and he wasn't ripped off, and, you know, the jeweler might have taken the gold and run off and bought his own little desert island and lived happily ever after, and give the king some fool's gold. So he had this problem. So he set this task to his population, his villagers or his peasants, whatever you want to call them, and his society. And he said, right, here's the challenge. If anybody can solve my problem, I'll be really happy, and you'll get this huge reward. So Archimedes was a mathematician, a physicist, I think, and he was sat in his bath contemplating this problem. How do I solve this problem? Because I know how to work out the density of gold. I need the mass divided by the volume. And if I know the known quantity, I know what the density of gold is, then I can compare the gold at the crown and see if it's actually made from the actual gold. Because I can, if the block of gold was a cuboid, I can do that. I can get a ruler, do length times width times height, get the volume, weigh the gold on some scales, work out the mass, and I can calculate its density. However, the problem was a crown does not have a regular shape. It's got a hole on the top, and then you might have little holes and funny little shapes in your crown. So it's not a thing that you can measure the volume of. So he had a problem, and he was sitting there contemplating, how do I solve this problem? How do I work out the volume of an irregular object? So he was there sitting in his bath while his bath was filling up, and he was contemplating it, and he was lost in thought and lost in concentration. How do I solve this problem? And as the bath filled up, you could hear the slapping of the water overflowing from the bath and landing on the tiles beneath him. Slap, 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 slap up. Suddenly, eureka, something struck him. He just worked out how to do it. And legend has it, he jumped out of the bath and ran down the street shouting, Eureka, 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 which means, I think, I've got it, I've got it, I've got it in Greek. I've got it. What has he got? He's probably got a chill from swinging in the wind, but legend has it he's ran down the street butt naked. We don't know how true that story is, but what has he got? What did he just work out? Well, he worked out this, that if that water is overflowing, so what about this? If I fill up a bath completely full of water with nobody in it, and I run the tap and it's completely full right to the edge and the water's not draining over, okay, you don't have that funny little overflow pipe. You could imagine just a tub full right to the brim of water. And then I go and sit in the bath and lay down in the bath, the water's going to rise and overflow. And he realised this, the volume of my body, which is an irregular shape, that sits in the bath, the water that overflows, that water is being displaced by the volume of my body. Which means if I capture that water that's been displaced and I measure it in a measuring cylinder or some kind of measuring device, I can work out the volume of the water. And that's how he did it, that's the eureka moment. He knows how to work out the volume of an irregular object. And we call that can, named after him, we call it the eureka can. Or sometimes we call it a displacement can, because the water is being displaced. So we call it the eureka can or the displacement can. How does it work then? So, your procedures then for measuring the density of regular objects, irregular objects, solids and liquids. These are the three practicals for the density that you must be able to do. We need, for all of them, a top-pan balance. That measures the mass of the object, not the weight, the mass, because weight is in newtons. It's measuring how many grams there are, the particles there. So for my regular object, for the first practical, you need to be able to write the methods for these practicals. So solid, you weigh it on a scale. Measure the mass in grams or kilograms. The volume, you get a ruler and you measure the length times the depth or the width times the height. Multiply those together, that will give you the volume of that. Mass divided by the volume will give you your density. The irregular object then, how do I do that? Well, here is my displacement can or my Eureka can. You get your irregular object like your rock, which hasn't got a shape that you could measure the volume of. And with a very thin thread, piece of string, because you don't want to make the results inaccurate, you place it into the displacement can. But before you do that, you need to fill up the displacement can full of water. And if you notice, as you fill up the can with water, it'll get to the top and then it will start to flow out of this little pipe here, this little spout. It'll flow out. So what you do is you fill it up until it starts to flow out. And then once the water stops dripping out, drip, 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 it'll get to this point here, this line here, where it's directly in line with that spout, just like the bath. Now as you place, now you take this away, you get a fresh measuring cylinder, because the measuring cylinder can measure your volume of your object accurately. You lower your irregular object, like your rock. If I just plonk it in there, you might get splashback, and then the water might splash out, so you might get inaccurate results. You lower it gently into the displacement can, and what happens as the water starts to rise, because of the displacement, the water will flow out of this pipe and into the measuring cylinder. And now you can take a reading, observe in the measuring cylinder the meniscus, so you get an accurate reading. And meniscus is now, if you look very carefully at the liquid, and you don't look from above and you don't look below, because if you look from above, the line might look lower than it is, and if you look from above below, it might look higher than it is. So you'll get a parallax error, we call it. You might read the readings wrong, the data wrong. So you got eye level, and you read it from the bottom of the meniscus, which is basically where the line, the water, it creeps up on the side. You'll see there's a slight dent up on the edges of the beaker or the measuring cylinder. So if the lines goes up slightly like that, you just measure it in line with that meniscus, and then you take your reading. Okay, and then you've got your volume. So what you do for the second practical then, for the irregular object, you first, don't put in the water first, because if you put in the water first, it'll get wet and you get a wrong reading on the mass. You need to first weigh the object, get the mass reading first. Always get the mass reading first. Okay, so weigh the object, get the mass, then place it in the displacement can. The displaced water, take the volume of the water that's been displaced. You do the mass divided by the volume, and voila, you've got your density. The third and final practical then, to finish off, liquids. And how do I measure the density of liquids? Well, it's actually straightforward. To measure the density of liquids, you need to know the mass of the liquid divided by the volume of the liquid. Well, the volume is actually really easy to get. Any liquid, whether it's oil, alcohol, water, golden syrup, whatever the liquid is, if you pour it into a measuring cylinder, you can measure the volume of that liquid. Simples, right? So there's your volume. It's the mass bit that gets people confused and tricky. I need to measure the mass of the liquid. Now I can't just pour it on top of the top unbalance, it'll just go everywhere. So obviously I can't weigh it. So the way you get the mass of the liquid is this. You get your empty measuring cylinder and you place it on your scales. So then you might have a number. Let's say the number is 10 grams. It's not the number, but let's just give you a number, easy number, 10 grams. So let's say you have 10 grams on there. Then you fill up your measuring cylinder with the volume you want, let's say 100 centimeters cubed of liquid. Now, if I go and put that water now on that measuring cylinder, on that top and balance, it might weigh 110 grams now. So if I want the mass of that water, I have to do the after mass, take away the original mass, the empty measuring cylinder, and that will give me the mass of the liquid. Because if I've got 110 with the water, but the empty one is just 10, that means 110 take away 10 gives me 100. So the mass of 100 centimeter cubed of water would actually be 100 grams. That's what I should get, okay? So there's another way you can do it, is these top unbalances are actually quite sophisticated, because you can weigh your empty measuring cylinder. There's a special button on these top unbalances called the 0 button, or sometimes it's called the tare. It's called tare, or the 0 button. You place your cylinder on there, it'll say 10 grams, then you press your tare button or your 0 button and it'll go 0, which is weird. How can it weigh nothing? It's because what it's done is, if I take that off now, it'll say -10. Put it back on there, it'll say 0. What it's done is it's zeroed it for you, so then when you pour the liquid in now, it'll give you the actual mass of the water. So when I put that on after I've tared it, it'll say 100 grams instead of saying 110 grams, because now you don't have to do that calculation. Now obviously the calculation is simple. You do one, take away the other, and it'll give you the mass of the liquid. And that's it. How do I work out the density of liquids then? Liquids is, I get the mass by measuring on the top unbalance, okay, by doing the empty one and the full one, take away the empty one, that gives us the mass, divided by the volume, just by reading the volume on the measuring cylinder, divide the two, and there, voila, you've got your density of your liquid. And that's it. So you want to put your results in there, write down what your liquid is, write down what the mass is, write down what the volume is, and then density divided by volume. And the irregular object, you do the same thing again. So same results table, the volume of the water that's been displaced, which is the volume of the object, the mass, write down the mass when you weighed it, write down what it is, like a stone, a piece of rubber, whatever it is, and you can calculate your density. So these are some of the practicals that we did in class. Here's a few little example questions for you guys to have a go at. You need to make sure you do the density practical. There are some YouTube videos out there where there are some teachers who actually do the practical for you. I'm actually at home, so I haven't got the equipment lying around. Weirdly, I don't live in a science lab, although you see me in science in school every week, when we're at school. I don't actually live in a lab, so I don't have the kit at home, but if I ever get a chance, I'll show you how to do that practical, either online or you'll obviously do it in lesson because you have to do the required practical. So what you need to be able to do then is, there's some results. I'm going to post this on Show My Homework, so you've got access to it. The most important thing is that you do the practical and you write that, you make sure you write down the methods. Okay, so you need to, for a 6-mark question in the exam, be able to write the method of how you measure the density of a regular object, an irregular object, and liquids. Okay, so, and then you can write a conclusion on how you can make your measurements more accurate, because you can use a ruler is accurate enough, but if you want to make it even more accurate, you can use these little pieces of equipment called vernier calipers, which measures it even more accurately. Okay, so here's some key points. Density is mass divided by volume. To measure the density of a solid object or a liquid, measure its mass and divide it by its volume. You can rearrange this equation like we talked about before, and if the density is less than 1 kilogram by decimeter cubed, or 1 gram per centimeter cubed, if it's less than that, it will float, and if it's more than that, it will sink. Okay, some exam questions for you guys to have a go at as well. But that's the end of that lesson. Hopefully you've learned something on My Smart Learning today. Hopefully you've taken care, and hopefully we'll see you very, very soon back at school. Keep up with your learning. And before I forget, if you got all 5 questions right at the beginning, I forgot to give you a virtual high five. So see you next time. It's a virtual high five from me.